Hello everyone, we'll go through Laplace transform today, and mainly we'll focus on introduction of Laplace transform and then going through the properties of this transformation. So first, what's this Laplace transform? Assuming we have a function f of t, and then we are trying to transform this function instead of a variable t, we are transforming this to the function of s. Mainly these the variables we are using in the Laplace transform, so this is T domain or some electrical engineering properties or some other things. We will use this as a time domain, and then S will represent the frequency domain. So what's the relation between this big F and small f? It's nothing but this f of s will be equal to the integration from 0 to infinity of exponential e power minus st multiplied by f of t dt. And then this is our Laplace transform. This is the integral form. One basic question is any function can get a Laplace transform 4, which is a very brilliant question. So not all function we can solve this integration from 0 to infinity, as we can see all there's here this infinite and the integration limits. So mainly we will focus on some basic criteria. This f of t, we call it will satisfy the condition of an exponential order. So f of t must be an exponential, to be of an exponential order, which means this f of t must be less than or equal any constant, positive constant, and multiplied by e power ct. So we call this f's exponential order c, which is this power here. So for example, over some basic functions, we can see e power t squared doesn't satisfy this one. E power t must satisfy this one. So all these functions are not of an exponential order. So this will give us some hint what these functions will look like. Again, let me repeat it here. We have function f of t. This function will be multiplied by exponential e power minus st, and then we will get the exponential multiplied by this function integrated from the range for the range from 0 to infinity, and then this will be our f of s. What kind of function we can use? There is a simple table which we'll go through this one very soon. So through the table, which we will have some function f of t, and it's required to find what's the equivalent f of s. If we have constant k, so this f of s will be k over s. If we have exponential with any exponent a multiplied by t, f of s will be this 1 over s minus a. If we have t, this f of s will be 1 over s squared. Generally, if we have t to the power n, and then n is a positive integer, so this would be nothing but n factorial over s power n plus 1, which is special case if we have t power 1, then will be 1 over, which is 1 factorial over s power n plus 1, which is in this case s power 2, which is s squared. Completing this one, we will have another thing here. Let's complete another basic function. If we have sine AT or cosine AT, or some case we have the hyperbolic sine, which is sine, or the hyperbolic cosine, which is cosine. All of them will have some numerator and denominator, so it will be some fractional functions. This will be a over s squared plus this a squared. Cosine will be the same denominator, which is s squared plus a squared. And here it's s in the numerator. Sine and cosine, it will be the same as sine and cosine in the denominator and the numerator, except this here with positive sign, here with negative sign, which can be concluded as this a over s squared minus a squared. Here will be s divided s squared minus a squared. This simply, we can see this sine. It's nothing but exponential minus another exponential over 2, and we have rules for the exponential. And this cosine is nothing but both exponentials added together divided by 2. So using this formula or using these from the table, we can conclude these values again. So let's go through some simple proof. If we have f of t equal to any constant k, k is nothing but constant, positive, negative, and like fraction, integer, doesn't matter. So f of s from the definition, it will be the integral from 0 to infinite e power minus st, f of t in this case, which is this constant k dt. And then k is a constant, so it will be besides this integral 0 to infinity e power minus st dt. And then the exponential is nothing but e power minus st divided by, we are integrating with respect to t, so it will be divided by minus s, and then substituting with this limits from 0 to infinity. Something to remember quickly: e power 0 is power 1, e power minus infinity it's nothing but 0, e power infinity it's goes to infinity. So here, this one will be s will be equal to k, and then e power minus infinity minus e power 0 divided by minus s. This one goes to 0, this one is 1, so it will be up with minus 1 by minus s, which is at the end, it's k over s. And this is the one we already got from the table at the beginning. So let's see another one. If we have f of t as exponential e power at, so again f of x is nothing but an exponential e power at multiplied by e power minus st, integration from 0 to infinity. We can go through these properties of the exponential. We will take t common, and then we'll get minus t common, and then we'll end up as minus a, and then this one dt. Why minus t? As we just remember together, we need to substitute with something that goes to 0, so e power minus infinity will goes to 0, so this will be much easier in the substitution. So f of s, again, it's just an exponential function, so it will be the integral of this exponential function, this exponential divided by this exponent, which is the number multiplied by t, which is minus s minus a. And then substitute with 0 and infinity. Again, it will be e power minus infinite minus e power 0 divided by minus s minus a, with this common minus here. Again, this will be cancelled, 0, this will be 1, and then we will end up with 1 over s minus a. And again, this is the one we got from the table. So, as we can see, we can move through all these functions, and we got this proof for what we already got in this table. So, what we can use from this one? At the beginning, there is some simple properties for this transformation or this integral. First of all, it's linear transformation, so we will anticipate that this linearity property will be here and will satisfy. And this is the case actually. So, for example, if we have f of t, having Laplace transform f of s, the linearity implies if we have this f of t plus another function g of t, so Laplace transform, let's assume this Laplace transform, this R do nothing but getting this Laplace transform, it will be this f of s plus g of s. So what happens if we have some constant here or here? So this will be, if we have any constant, multiplied by these functions. Again, it's nothing but an integral. So the constant will be outside the integral, where will be ended up with the same thing. So the same constant and same f of s, and g of s, it will be the transformation of the g of t, and b, it will be a constant, and this plus sign. So after all, if we have minus sign, it doesn't matter, it will be minus. So if we have any kind of linear combination of functions, so Laplace transform, it will be the same transformation for this linear combination. We have function, because this Laplace transform, another function, this is Laplace transform, and the constants will be the same with no change. Another property, which is, can call it shifting, or multiplication by exponential. What does this mean? If we have function f of t, and this function has the Laplace transform, which is f of s, if we are multiplying this function by exponential, we don't need to go through the whole steps for the integral. Just Laplace transform from this property, it will be nothing but this f of s, but instead of s, make every s minus a. How we can do this thing to be proved? It's very easy. So let's assume if I have f of s, it's from the definition of Laplace transform e power minus s t f of t dt. So what happens if we have this one here, e power at f of t dt? I am just adding this one here, and the same exponential for this definition, and the integral from 0 to f. Again, just put these together. So this one will be 0 to infinite e power minus t, and then there's s minus a, and f of t is the same dt. And then we can end up with this f. If it was previously f of s, we'll have this s here for the exponent. So what happens if we have the same everything? We have ft dt. Yes, we have the integral from 0 to infinite. We have this one again. And instead of this t minus t multiplied by s, this minus t is multiplied by s minus a. So whatever called previously as f of s, this is nothing but f of s minus a. So this ends up, if we have integral e power minus st e power at f of t dt. So if we are multiplying by exponential, on the other hand, just this one will be shifting in the S domain, which is the name of this property, which you are doing shifting, or multiplying by exponential on the other hand. Just a quick example for this one. Let's assume I need to get Laplace transform of e power minus e power plus 2t multiplied by t. If we need to get Laplace transform something like this, let's see where this comes from. So first, from the table, we have f of t, we have f of s, we have basic function k constant, we have t, we have exponential, we have sine and cosine. So in this case, we have this one was k over s, this one 1 over s squared, this one 1 over s minus a. Again, the property right now, if we have multiplication by exponential, which is the case right now, we have exponential multiplied by a function, and this function already in this table here. So first, we can call it in this way. This is Laplace in French, so this is Laplace of this function alone. It will be 1 over s squared. From where? From the table. And then, from the properties, if we have Laplace of this exponential multiplied by this function, so the shifting property says if we are multiplying by exponential for this function here, this will do something very similar. It will be shifting. So this exponential, it will be s for this function, and just this exponential will do the shift. So this means I will have the same 1 over s squared, but this exponential will do nothing but shift this s with the same value. So this s, instead of s, it will be s minus 2, and the whole bracket squared. And that's it. So this one right now, again, we have Laplace of t is 1 over s squared. This is from the table. And then this t, here we got this 1 over s squared. And then this exponential will do the shifting properties. So the shifting property, it will do nothing but s will be s minus this number multiplied by t. Okay, let's move forward. The third property, which we'll have here if we are multiplying by t. If we are multiplying by t, means if we have Laplace of some function f of t, that's f of s, and then it's required to get this Laplace of the same function, but just multiplied by t. This will be minus the derivative of this function with respect to s. Generally, if we are multiplying by another t, it will do the same thing. It will be the derivative and multiplied by minus sign, which generally, like if we multiply by another t, it will do nothing but another minus sign. And instead of the first derivative, it will be the second derivative, which is generally, we can generalize this one, t power n, f of t, it will be minus 1 power n, and the derivative for this n. So this is the property. Also a quick proof for this one. Let's see. So we have fs. It's all from the definition. U to infinity, e power minus st, f of t dt. It will be the opposite thing. So let's assume, and this is the easier time, the easier thing to prove. What about if we need to get this derivative? The derivative is nothing. It will be the derivative of the other side. e to infinity e power minus st f of t dt. Again, we are doing integration with respect to t, or differentiating with respect to s, so we can move this the derivative inside the integral. So this will be 0 to infinity d by ds e power minus st f of t dt. There is nothing include s in these functions except this one. So the derivative of this one, it will be 0 to infinity. Derivative of this one with respect to t, it will be minus t e power minus st. Derivative with respect to us, it will be minus t e power minus st f of t dt. Just rearrange these terms together. It will be from 0 to infinity e power minus st t f of t dt, and there is minus sign. So if we are moving with this minus sign the other side, it will be minus df by ds equal 0 to infinity e power minus st t f of t dt. And it's nothing but Laplace transform of anything. It will be anything multiplied by the exponential integration from 0 to infinity, and this integration will be Laplace transform of this anything function. So this means Laplace of t multiplied by f of t, it's nothing but f of s derivative with respect to s multiplied by minus sign. And this is simply the proof of this property. Let's see a sample example applying this property. Again, if we have, I need to get Laplace transform of t multiplied by e power 2t. We did this before using shifting property, but right now we can use multiplication by t property, which we can start from. We all know that e power 2t has Laplace transform 1 over s minus 2. And then, if we are multiplying by t from the definition, it will be nothing but minus derivative of this f of s, which is the derivative of 1 over s minus 2, which is minus sign, and then this derivative of this fraction could be this one squared. There is minus 1. The minus sign will cancel out each other, and then it will be 1 over s minus 2 all squared. And this is nothing but the Laplace transform of this function. We get this before? Yes, we did this using the opposite thing. From t, it's 1 over s squared, and then this exponential here will do the shift, so it will be minus 2, and then comparing both terms, can get this one equal to this one. So you are free to use which property, but on the other hand, make sure that t is just one derivative. Exponential will do this shifting. If we have t power n and the exponential, for sure, we can avoid moving through this whole derivative loop and then easily get whatever is the function here, which is t power anything, as the Laplace transform of this function, and the exponential easily will do the shift. So you have the freedom to choose which one you are more comfortable with, and both for sure will be ended up with the same result. Again, let's move with this one right now. Is the fourth property, which we already completed the linearity, the multiplication by the exponential, the multiplication by t. Now what happens if we are doing this division by t? So if we have Laplace transform of any function, can easily obtained, which is there is a function f, capital big F of s. So what happens if we have this f of t divided by t? For quick comparison, if we are multiplying by t, we have this derivative with respect to s. So this will be the opposite. So this one will be integration of this f of s with respect to s, but I will put it with another parameter, another name, as we have this limits for this integration from s to infinity, just not get confused with both s. So a quick example of this one. If we have Laplace of sine 2t over t. From this definition of this property, so it means you will need to get the integration from s to infinity due to this t in the denominator, and then Laplace of this sine 2t, which is 2 over s squared plus 4. This is from the table. So we know this from the table, which is the sine, and then we continue integrate this with respect to s. Integration this with respect to s, so this is the inverse tan, so this one will be the inverse s over 2, this 2 here divided by 2. And then we'll substitute s infinity. Again, just for confusion, we can assume these parameters here is this one is u, this one u, and then u. Just a little bit confused with both s. So this 2 is to cancel out, and then we'll end up with tan inverse infinity minus tan inverse s instead of this u, so s over 2. So again, just a reminder for this tan inverse property, so the angle would have tan inverse infinity, which is in radian pi over 2. Tan inverse, if it's 0, so this is 0, the smallest angle that has this 0 value. And by the way, tan inverse 1, which is 45 degrees, which is radian pi over 4. So let's turn back to this one. So Laplace of this sine 2t over t equal pi over 2 minus tan inverse s over 2. And then this is the result. So this one will be very helpful if we have any function divided by t, so we can go through this one with this way. So again, let's go to the other property, which is right now move through properties division by t, multiplication by t, the exponential multiplication, and the linearity. So the opposite way, if we have derivative with respect to t. So again, we have function f of t, and then Laplace transform f of s. What happens if we need to get Laplace transform of this derivative f dash of t? How this will look like? This will be nothing but s multiplied by f of s, and then minus this term with f of 0. This small f, it means this is the value of f of t at t equal to 0. So again, what happens if we need to get the higher derivatives? What happens if we need to get this f double prime? So the second derivative will have Laplace transform, which is s squared, this multiplied by the original function f of s, minus s f of 0 minus f dash of 0. And then this will be the rule for second derivative, and this is the rule for the first derivative. So again, generally speaking, if we have the nth derivative t will be the same power as we can saw from both examples, multiplied by f of s, and then we'll move through this s n minus 1, f of 0, and then we'll keep going until the n minus 1 derivative of the function at t equals 0. So this will be very helpful in solving differential equation. And this is something very important. So in solving differential equation, previously we need to go through integral and different methods, but right now we can get this derivative, and instead of d by dt, d by dx, all these derivatives, and then the opposite, it will need integrals. Right now it's just algebraic equation, which you just need to addition and subtraction, which is one of the best benefits of using Laplace transform of all kind of solution. So this will go through this with more details and using this in the differential equation. But right now, let's move forward to the last property today, which is, again, let's recap. We have multiplication by t, we have division by t, we have exponential multiplication, we have the linearity, and we have the derivative, number 5, and what about the integral? So the last time today will be integral with respect to t. Again, we have f of t will be, this f of t will have Laplace transform of s, and then what happened if we have integration from 0 to t of this f of t dt. Again, just to make sure that there is no confusion, if we have this limits of t, so this any function is another variable, this will be ended up with this just f of s divided by s. So again, I could example this one. If we need to get the Laplace transform from 0 to infinity, for example, we have e power 3t, and then this multiplied by t dt. So, sorry again, this one here from 0 to t. And again, to put it in the right form, e power 3u, u integration with respect to u. How can we get this one? We can see, like we have 3 different properties, we need to use 2 of them and 1 from the table. So first, we have this u, which is t in the time domain right now. We have this exponential, we have this integral. So this one will be divided by s. This one will do shift. This one will do the derivative. So assuming these poles, again, for the easier, in my opinion right now, just to go through this u from the table, and then the shift will be much easier. So first, let's get Laplace of u from the table, it's 1 over s squared. Don't forget this u, it's nothing but it's the same t. And then Laplace of this e power 3u multiplied by this u will do nothing but shift every s will be as minus 3. So this one will be as minus 3 squared. And then we will end up with this one. So Laplace 0 to t of this whole function e power 3u du will be nothing but Laplace beta, Laplace of this whole term divided by s. Laplace of this term, we already got it here, which is 1 over s minus 3 squared. So this is the denominator, so put it the right way, so 1 over s multiplied s minus 3 squared. And then this will be the answer of this one here. So taking this into account, we have, again, we have function f of t, and then this function f of t, we started to get Laplace transform for it, and then we saw what's happening if we multiply by exponential, if we multiply by t, if we're doing some derivative with respect to t, if we integrated from 0 to t, all these properties, besides the linearity, if we have addition or subtraction, so these the main properties to go through this one. And sorry, and there's another one, we have multiplied by t and we have divided by t. So we have 6 properties, and we moved through all of these ones. And finally, thanks for listening to this one, and we'll move forward to the next lesson, how to using these properties to get Laplace and moving from the s domain back to the time domain. And finally, thanks everyone.